Welcome everyone to this part 3 of our current series on best practice statistics with collision data. Today we're joined by TRL and we've got Ilaria and Themis who are going to be presenting to us about statistical tests in transport safety with a specific focus on surrogate measures. So looking a bit beyond our traditional Stats 19 kind of outlook. For those of you that missed the first couple of parts of this series and are interested in catching up, I'm just going to put a link in the chat where you can find all of our previous webinars that we run as part of the Road Safety GB webinar series. And the last two parts should be on top of that list there. Great. So as usual, please do put comments in the chat as we go, and also questions in the Q&A. We should have a bit of time at the end for questions for Ilaria and Themis. But otherwise, let's get started. So over to you guys.
Hi everyone, I'm Ilaria and I'm from TRL. I've been at TRL for 1.5 years now, and I'm a senior consultant in the safety team. My background is pretty much statistics and numerical and data analysis. So yeah, this is my, I guess, day-to-day job. Themis, if you want to introduce yourself briefly.
Yeah, hi, I am Themis. I've been with TRL in the safety team as a safety consultant since February, so a bit less than a year. My background is in physics, but yeah, I also work with statistics on my day-to-day, work.
So surrogate measure, why do we care about surrogate measure, what they are? So surrogate measures are indicators that are linked to the likelihood of a collision to happen. And they're really useful in the transport industry as a proxy of collisions. As we are all aware, the collision data can be sparse or rare, so it's quite difficult sometimes to analyze collision data, and that's where the surrogate measure comes to hand. They're also helpful because they are proactive, so basically we don't have to wait for a collision to happen, but we can analyze those metrics that are related to collisions, but they're not necessarily a collision. What are some examples? Some examples are reported here. There is a vast literature of surrogate measure and also some interesting debates on what those are. But one useful one is time to collision. So if we imagine that two vehicles are going on a direction and the speed is constant, so that's the time necessary for a collision to happen. So if they don't stop or there is no change to the speed, that's the time for if they were to be on the same trajectory. There is also like the post-encroachment time, which is the time between one vehicle to leave a spot and another to arrive at the same spot. Deceleration to avoid collision. The name here is quite indicative, so it is the deceleration rate in order for a collision to be avoided. And then we have the maximum braking deceleration. That's the highest deceleration observed during a potential conflict. So we feel that the common ground here is the conflict, so we often spoke about conflict. The gap time is, or the headway is the space or the time in between two vehicles, and we have the speed differential. That's the difference in speed between two vehicles. So those are some of the surrogate measure, but we can think of surrogate measure pretty much anything related to near misses or the speed, anything that can relate to a risky behavior and is linked to a collision. Where do they come in place in statistical testing? So as we mentioned, the collision data may be inaccurate or infrequent, so we may want to use some affirmation. We may want to confirm an affirmation around those. And as I think Oscar mentioned last time, we don't have to directly jump into statistical testing. So apologies if we are doing so just for the purpose of this. But the idea is to look at the data first. So we want to look at patterns. We want to look at, is there something that we want to verify? And the idea of statistical test is we start from an hypothesis that is the baseline. So we have an idea that's of the reality, and we want to verify that. We want to verify if there's been a change or if two scenarios are different. And I think it's important to stress that we are working in a probabilistic environment. So we are not in a place where we can say this is true or this is not true. So we don't observe the picture as a whole, but we observe the part of it. So we take a sample and we want to check if our sample is reflecting the null hypothesis or the hypothesis that we have in mind. So yeah, some uses are, checking difference between groups or checking the before and after intervention, for example. So we have two kind of statistical tests. So we have parametric statistical test and non-parametric statistical test. And we can think about those as a more precise, detailed hypothesis that we have will be a parametric test where we want to specifically test a metric or test something more specific, while the non-parametric test is more general idea, more general hypothesis that we have. And as I mentioned before, we are working in a probabilistic environment. So we often talk about p-value, and it's important to understand what this p-value is. And the p-value is the probability of observing the data if the null hypothesis is true. So if we get a really small p-value, rather than thinking that this hypothesis is still true, we rather go with the alternative hypothesis. That's why when we see a low p-value, we reject the null hypothesis in favor of the alternative hypothesis.
Can I just add to that, Ilaria? So you've obviously introduced the terms parametric and non-parametric tests here. So for those of you that are wondering what those kind of mean and where they fit in with statistical testing broadly. So last time Oscar talked us through a few methods for stats testing that he's doing in Devon, looking at collision data. And those of you that were there might recall that he said he uses Poisson tests, and also I think he mentioned chi-squared tests as well. So stats tests can be grouped into those two categories. They're either parametric or they're non-parametric. Poisson tests are an example of a parametric test. Chi-squared tests are an example of a non-parametric test. And if you're trying to choose which stats test to use, then you'll often go through the process of figuring out, can I use a parametric one or do I need a non-parametric alternative? So that's where it kind of fits in with stats testing.
Yeah, I think Themis will go into a bit more detail, but just to add to that is parametric will be where we have an idea, a more precise idea of what distribution the data follow, but we want to specifically verify the parameter of that distribution, whilst non-parametric one will be more wider, perhaps on a distribution, if it's a normal distributed or not, or if there is any kind of association between two variables, for example. But it's not that specific on one single parameter. That's why parametric versus non-parametric.
So yes, picking up from this conversation, when we want to identify what data set we have, we first have to identify its normality. So if it's parametric or non-parametric, as it has been discussed. So as we have said, parametric tests usually rely on the population's parameters, meaning its mean or its standard deviation, and they're looking for a specific value, so a parameter. A non-parametric test, in general, is less statistically powerful compared to a parametric test, and it differentiates on medians and ranks, not so much on means. In general, they check if there is a generic affirmation between the data sets. So What is normality? Well, normality is whether data follows this normal distribution or this bell-shaped curve that you can see in the screens. So a normal distribution, you would see a peak, while a non-normal distribution, you would see variable peaks or skews or data being scattered around. Why is this important to know what if your data is parametric or non-parametric is because they follow different assumptions, and these different assumptions will help you later on identify which test is more appropriate to use. So yeah, the data that follow, the parametric data follow the assumptions such as normal distribution, homogeneity of variance, and independence on observation. And non-parametric data follows the assumptions of independence, random sampling, and homogeneity of measurement, but they do not follow the assumptions of the parametric data. So this is just a cross table to give you an idea of a few of the statistical tests that are available. There is many more of these, but this cross table helps you with some most commonly used. According to the data that you have, the data type, so if it's normal, non-normal, nominal, or categorical, or count data, and according to the distribution of the comparison that you want to create, that you want to do. So if it's two groups, if you're comparing two groups, two or more groups, or if you are interested in the regression modeling, these are examples of a few tests that are available out there. Today, we're going to talk more about the t-test, the chi-square test, the ANOVA, Kruskal-Wallis, and we're going to touch upon modeling a little bit later.
Yeah, if I could just add to that again, Themis, if you go back a slide. Thanks, Ilaria. So yeah, I mean, this is a really nice table that kind of categorizes some of the different approaches that we can use. And combined with the previous slide that talks about parametric and non-parametric, I think those are probably the first three criteria you might use to decide on your approach based on the data you've got and the kind of question you want to answer. Firstly, can you use a parametric test or do you need a non-parametric test? And kind of combined with that question, what type of data have you got and how many groups are you trying to compare? And if you can answer those three questions, then usually you land on a particular kind of test or a particular kind of approach that you can then do. So that's maybe your initial decision-making process. Thanks.
Yeah, no, exactly. Depending on how many groups you want to compare, or if you have parametric or non-parametric data, you can select the appropriate test. To start off, I'm going to describe the t-test. The t-test is a parametric test used to compare the means of two independent groups. Its aim is to determine if there is any statistical significant differences between these two groups. As Ilaria spoke in the beginning about null hypotheses, the null hypothesis in a t-test would usually say that the mean of your group A is the same as the mean of your group B. Then for t-tests, we have two types of alternative hypotheses, and these are bilateral or unilateral. Bilateral is where the means of group A and group B are not the same, and then a bit more detailed is with unilateral, where we can identify if the mean of A or B is smaller or equal to the other group. This follows some assumptions. The assumptions are if the data is approximately normally distributed, if the groups are independent, and if the the variances are equal. Now that we have described a bit the test, let's get some surrogate data and ground it with an example. So in industry, it is commonly used. The t-test is commonly used to compare average values or means of speeds, times before and after interventions or between sites. So an investigation that TRL has conducted was on the means of speeds after a safe intervention has occurred in a specific place. So the null hypothesis in this investigation was that the means of speeds before and after the safe intervention will remain the same, so that nothing has changed. So with Compass IoT data that has collected the speeds of vehicles at an intervention location, we can see from the graph a bell curve, so we can see that it is parametric. But we would expect that after a safe intervention has been placed, that the mean of the speeds would be lowered. However, as you can see from the dotted lines, the blue one and the red one, they're pretty similar to each other. And this shows that the null hypothesis is true. So we accept the null hypothesis that the safety intervention did not change the means of the speeds. However, if we wanted to go a bit more in detail and to confirm what we see graphically, we would do the t-test and find the p-value. And here we can see that in the black box, you can see the mean speeds of 33.46 and 33.89. And you can see that the p-value is 0.09 ... And you can see that that is bigger than the 0.05 threshold. And therefore, we see that there is no significant statistical difference between the speeds.
Just to add to that, again, in this case, probably we didn't really need a test because it's quite evident from just a first look that there was not much of a difference, or even if there was a difference, it was not to that point that you would have expected. So, this is one case where we performed the test because this was it was a set of tests. So it wasn't just this on isolation. This is just an example. But this is a specific case where, you may want to stop even by looking at the graph. It's quite evident that those two sets of data are quite similar. So, okay, so one more example of t-tests is on the time to collision. So in here, what we want to do, we want to compare two different design of a road and check the time to collision. This is data from a simulation. So because this is data to simulation, we are pretty confident that we can basically have multiple data, and we are quite confident with the normality being expected in this case. And if we look at those scenario, we can see that there are different results based on the threshold that it was set. So we have design A and design B, and we are in position where design A is significantly different in terms of time to collision to design B in the first occasion, but it is not if we set a lower threshold. We also did more studies, like we had a study where we had to check the time to reaction. This was a study that we conducted with DFT, and this is quite similar, where we wanted to, in this case, it wasn't two different design, but it was two different groups. So we wanted to check the time to reaction to another between learners driver and experienced driver. And in this case, we also adopted the t-test, and we found that there was a statistically significant difference between the two groups. Okay, another test that we use often is the chi-square test, and this is quite useful to assess the association between two categorical variables. So the categorical variables are variables for which we have categories. So this test is usually used on frequency tables. So we usually have cross table, and we want to assess if two variables are related. And we want the counts ideally to be, for its frequency to be higher than 5, and it usually works better with larger samples. So what's the idea of this chi-square test? The idea is that the difference between what we would expect if the data was, if we had two independent variables, if we had no associated variable, will follow a chi-square distribution. So when we perform the test, if the result is on the left side of this graph, then we can say that there is no association between the variable. If we found that we are on the right side, then we have found some association. So to just give you a more practical example, this is something that we may want to use. So we are basically thinking about cross-tab of frequency. So in this case, we want to assess if there is a relationship between the age and the driver behavior. And what you see on the top figures are the observed values, and what you see in parentheses are the expected values in under the assumption of no association between the variables. And what the test does, it basically checks how distant those are, so how distant the observed values are from the expected values. And if those are not distant enough, then we are under the assumption of no association. Otherwise, we may want to reject this hypothesis and say that it's an assumption. And I think it's important to stress here that we're not checking in this case any causality, like we are only saying that there is an association. If we want to check which variable drives the other, more further tests are needed.
Yeah, can I add to that, Ilaria? If you just go back a slide, sorry. So I think I mean, you picked up on this a few minutes ago with the t-test as well, but the eye test is really important, I think, when you're doing stats, because really you shouldn't be surprised if your stats test comes out as significant. You should already be partly expecting it based on what you see. And obviously here you can see in the lane category on the right hand side, that typically has lower numbers than the other categories, and it doesn't really look like there's much of a relationship between the behaviors on the top and the ages down the side. The distributions are a bit different, but there's nothing particularly interesting going on. And similarly with the t-test, with the speeds, the averages were so close that you wouldn't really expect to see stats test come out as significant. So it's always worth, before you run your stats test and look at your p-value, consider what you expect to see based on the data. And if you're surprised, then it's worth a question of, okay, why did that come out significant, or why did it not?
I think it's also important to consider how many data points you want, because just considering a different field, for example, a medical field, like a tiny, small difference may be significant, and we want it to be significant. We want to see that difference, even if it's small. So I think that's something else to consider, and how much data point is actually needed for your analysis. That's just something additional that you may want to think on.
If you have a big sample, it's much more likely to be significant because you've got more data that's more reliable. But with a smaller sample, you're less likely to get significant results. So yeah, definitely that's something else to consider.
So another statistical test that we can use data to analyze data is ANOVA, or otherwise known as analysis of the variance, which is a parametric test, and it's usually used to compare the means across 3 or more groups. It checks if at least one of the group means is significantly different than the others. There is 3 types of ANOVA tests. There is the one-way ANOVA, which has one independent variable, two-way ANOVA, which is 2 independent variables, and repeated measures ANOVA, which has the same subjects measured multiple times. The assumptions, such as with many other parametric tests, remain in the similar lines of normality of residuals, homogeneity of variance, and independent observations. Yeah, and now this diagram to explain a bit more about how ANOVA works. So this diagram illustrates the concept behind ANOVA, which is used to compare means across multiple groups. It checks the variation between the groups, which is the orange line that you will see. This measures how far apart the group means are from each other. If this variation is large, it suggests that the groups differ significantly. Then it also checks the variation within each group, which is the red lines. This represents the spread of data points inside each group. A high within group variation means that the data points are widely scattered, making it harder to detect differences between groups. Then the total variation, which we'll see in the blue line, this is the overall spread of the data points across all groups. ANOVA partitions this total variation into 2 components, the same 2 components as above, the between group variation and the within group variation. And the key idea is basically that the ANOVA tests whether the between group variation is significantly larger than the between group variation is significantly larger than the within group variation. And if so, that means that the group means are likely different. Again, another practical example is an investigation that was also conducted by TRL, with the surrogate data being the calibration. Sorry. Yes, so we were investigating the advanced driver assistance systems, ADAS systems, through various calibration tools. And the surrogate data for this one was the warning distances from these tools. So we were comparing the means of these warning distances with an null hypothesis that the mean value of each calibration system remains the same. We have created box plots for these different groups. So you will see the gray group, the orange group, and the green group. And then basically, you will see that there is a variation between the means. And while conducting ANOVA will tell us that there is a variation between the means. With further testing, we, as you can see down in the table between group and p-value, further testing can be conducted to find the p-value of each individual group and then indicate which group is responsible for the variation in the means. And as you can see here, in red, the SCT group is the one responsible for the variation in the means.
Another test that we can use is the Kruskal-Wallis. And again, we are here in the scenario where we have more than 2 groups. It can be 3 or can be multiple groups. And basically, this is a non-parametrical test because it's not checking on a specific parameter, but we may think about it as it's checking on the median. It's just for simplicity, it's not really checking on the median, it's more checking on the distribution and the ranking of the distribution. And to get this with a visual example, we can think of the scenario that we were analyzing before. Like, let's think about time to collision, and we have 2 different scenarios. In the scenario on the left, we have non-significant results, so the distribution are quite similar, and on the right we have significant results. Why we may want to use this? We can see that the data points in here are really small in small sample, so we don't have the luxury to utilize the any parametric tests in this case. So we want to rely on this test instead. So we introduced the statistical test and kind of hopefully give you some more direction into how to decide on which one is the one to choose. A wider idea is statistical model. When we want to use statistical model is to understand a phenomenon rather than verify an hypothesis. So it's a wider scope into assessing relationship. So we have an independent variables and we have dependent variables that we want to assess a relationship. So we have an outcome variable and we have predictors. So it's used for different scopes, and it can be used for exploring a phenomena, or it can be used to make predictions. So we may imagine a different predictor changing, and we want to see what's the results. And also what's important here is not taking one variable at a time. The model is usually used by considering multiple variables at the time. So we have one outcome variable and we have different predictors that we think are related to that variables. We have different type of model, and I think just again, to give you some orientation here on which one is the correct model to use, I think what's the first question that we may want to ask ourselves is, what's the nature of the outcome variable? So the outcome variable may be of different nature. So it may be a continuous variable like the speed or the time to collision, for example. In this case, we want to use a linear regression. There are different reasons why we may want not to use a linear regression, but the first point is always kind of, to get an idea, will be a linear regression if we have a continuous variable. And there are many assumptions, and we may be flexible or not flexible with this assumption. We mentioned last time that we assume the independent in observation, and this may not be true, but sometimes we may want to be flexible with this. We assume linearity, so between the variable, the predictor, and the outcome variable, there is a linear relationship in this case. And also we assume that when we build our model, some part that is not explained, so those are the errors, there is normality in errors, and there is no difference in the variance of the residual. Instead, if we have a different outcome, which is a binary outcome, for example, how severe is a conflict, we may want to use a different model, in this case, the logistic regression. So this is more suitable where we have a yes or no outcome. And again, we have some assumption here, like again, the independent observation, and also the linearity between the predictors and odds. In this case, what's the probability of the event to happen compared to the probability of the event to not happen. And other models that we may want to use, we use those a lot, are counts models, so Poisson model and negative binomial. And again, we may want to use this where we have frequency to assess. So for example, number of conflict in this case. And the difference between the two are that the Poisson model assume the mean to be equal to the variance, but often this is not the case. So often we found in our data there is over dispersion. So we may want to use instead the negative binomial.
So as you can already tell, surrogate data are very useful in analyzing safety conditions without waiting for actual crashes to occur. But we need to make sure that these data are valid, and this can happen through various methods. So validation methods such as correlation with crash data, where surrogate data shows strong correlation with the actual data frequency and severity, can be used. Simulation versus field data, where the data is validated from traffic simulations against real-world observations. Sensitivity analysis, where it tests how surrogate measures respond to changes in design or traffic flow. And cross-method comparison, where it compares results from surrogate-based models with traditional crash-based models. And we also have to be aware of its limitations, as we have assumption proxies of accuracy, where surrogate measures assume near misses and predict crashes, which may not always hold. Data quality issues that requires high-resolution video or sensor data, where errors in detection can affect reliability. Context-specific measures calibrated in one region or traffic condition may not, generalize. Rare events bias, surrogate may not capture extreme crash scenarios, and interpretation complexity, as multiple surrogate indicators can conflict, which require expert judgment. And I can appreciate that it might be a bit much to remember all of these statistical tests, especially in a 1-hour webinar. But it's important to highlight that the statistical analysis is essential in interpreting surrogate safety data and any data for that sense, and guiding evidence-based road safety decisions. The selection of appropriate tests ensures methodological rigor and ensures the reliability of safety assessments. Surrogate measures, when analyzed correctly, offer valuable insights into potential crash risks without waiting for actual incidences. And lastly, by integrating tested methodologies and robust statistical tools, transport safety research can be both proactive and scientifically sound.
I think we just reported some reference here. So yes, this is us. So if you want have any question?
Great. Thank you so much, Ilaria and Themis. So you've just taken us on a journey there, thinking about different surrogate measures like time to collision, speed, etc., rather than crash data. You've taken us on a journey of how you can use different stats testing and stats modeling approaches to answer questions about those surrogate measures. I wonder if you could just summarize some of the decision-making processes again, in terms of if I've got some data and I want to understand how can I analyze it statistically, or how can I use statistics to support what I'm seeing, and I have to decide, do I need a stats test here? If so, how do I choose which one? Do I need to use some modeling? If so, how do I know whether it's linear regression, Poisson regression, another kind of regression, or a different kind of model altogether? Yeah, can you talk us through maybe that decision-making process at a high level, and maybe a few examples of things that would fall into different categories?
Yeah, sure. So I think the first thing to say is what's the question? So what's really the question? What are we trying to check with the available data? So is there that we want to verify a simple hypothesis? So we're not interested into looking in the wider factor of like the phenomenon on a whole. We want really to be specific. I think Oscar last time showed a really specific question that were coming through to his inbox to answer, like is the speed decreased in this particular location? So you can already have a sign this is quite specific, because it's more a yes or no question. So it's kind of like, how do I make a decision to assess if this is true or not? So this is the first point, and I want to go with the statistical test in here. So we already have a baseline here. So we already have an idea of the distribution. Perhaps we just want to see if the mean is what we would expect, or is it different? So in this case, I would go with statistical test. It's a simple decision that I have to make. Is this affirmation true or not true? A model is something wider, as I tried to describe. So when we utilize a model, we want to understand we have more uncertainty, I guess. So we want to understand the phenomenon, and we want to see what really affect, what influence that specific outcome. So we may want to analyze different variables, different factors, and check the relationship between all of those. So this is the first direction. And then in terms of what utilizes, really comes down to checking the data and assessing what I'm dealing with. Is a continuous variable, is a categorical variable that can give some of that. It's quite wide argument in here, but yeah, this is the first step that I may want to go through. Does it answer your question, Nathan?
Yeah, I think that answers my question. I wonder if we could get a bit of audience participation at this point. Actually, I've noticed a question has gone in the Q&A. But if you're somebody that does stats testing regularly, or that builds stats models regularly, could you put in the chat what test or what model you've used and what question you tried to answer with that model? So it might be, I use stats testing or I've used t-tests to look at speeds before and after an intervention, or I've used stats models or linear regression models to look at the relationship between different variables and speeds.
Sorry, Nathan. And sometimes we don't really know before we check the data. Like I was describing the difference between Poisson or negative binomial. And we know probably from experience that we, most of the time go to the negative binomial, because the hypothesis mean equal variance is quite hard to verify, but we may want to check this in our data. So this is an additional test in this case that we may want to perform in order to answer that question. It's not always straightforward, is my message. That's why, and also we operate on a probabilistic environment. So we may want to check if the assumption is true or not.
Great. Thanks, Oscar, for kicking that off. Please do keep putting examples in the chat. I'm interested to understand what stats tests you're using and particularly the questions that you're answering with those. I think my classic go-to examples, if I'm trying to describe what I might use a stats test for, it's we've had some kind of speed intervention, put in a speed limit sign or something, or other traffic calming measure. You've got measurements of speeds before, you've got measurements of speeds after. That lends itself really nicely to a t-test or a non-parametric equivalent to see if there's a difference in the before and after speeds. And then in terms of models, it tends to be, I want to understand what factors are influencing crash risk on these sections of road. And Poisson models are really nice for understanding collisions because Poisson models are for count data, so numbers of things. And collisions, of course, you don't have half a collision, you can't have a negative amount of collisions. So it lends it really nicely to that. So using a Poisson regression model to understand the relationship between different factors, speed, infrastructure quality, traffic, presence of a median barrier, those kind of things, and crash risk is quite a typical one. Okay, we've got a question in the Q&A. I don't think this is an easy question, but I'll throw it at you and see where we go. Would you know if surrogate data has been used in crash prediction and then in design of countermeasures in the UK? Take that as you will.
I think, there are different arguments on this, and I think Themis showed some of the limitation as well. I think it's quite useful as first step, especially with the simulation that, in the simulation space, you may want to build different scenario. But I really don't know if this has been used in this case, but yeah, it's something to reflect on, I guess, because I think if we look at the literature, there are many examples and some argument against it too. But it's definitely something to consider where the data is limited. So if we don't have a place to start, then probably it would be worth considering surrogate measure, I'd say. Especially if we are looking, like a limited location or limited time. In this case, we may think the collision is really not there, likely. So then we may want to use surrogate measure. That is my view, at least, but I'm not sure.
Yeah, I can maybe build on that and give you an example with a DPAC. Yeah, where I've used surrogate measures before, where collision data wouldn't be appropriate. So some of you might be aware of the Helm UK project that ran a few years ago, and I worked on that with a number of colleagues actually when I was back at TRL. And that project involved looking at trucks platooning on motorways in the UK. And by platooning, I mean basically 3 trucks traveling close together, closer than your standard safe headway, but using coordinated braking and acceleration to almost kind of travel as one body. But with those reduced headways, the idea was that you'd potentially save fuel and have other benefits. But anyway, to assess the safety of those trucks on the network as they go up and down the motorway, using collisions wasn't really appropriate because for a start we weren't expecting them to be involved in any collisions, but also the time period just wasn't long enough for that to be reasonable, and so to get a kind of operationalization of safety in that case, what do we mean by it? We use surrogate measures. So we measured time to collision, we use post encroachment time, a lot of the measures that Ilaria referred to at the start of the presentation, as a bit of a proxy for safety in that case. And there's lots of evidence in the literature. I think some of the links you guys provided in this presentation as to why time to collision, post encroachment time, and other surrogate measures are a good proxy for collision risk. But we measured those things, and we had hundreds of incidents where the time to collision was below a certain threshold, or the post encroachment time was below a certain threshold that starts to mean it's kind of getting towards an unsafe situation. And obviously you filter out things that are maybe false positives, like maybe braking just before a traffic light or that kind of thing. But in using those and doing stats tests on those surrogate measures, you can get a much better picture of safety than waiting for crash data or similar. So I think those kind of on-road trials or real-world trials of things, and even through simulations, using these kind of measures is a much better way of getting a sense of how safe something is. Great. Hopefully that helps. I don't believe that nobody here, apart from Oscar, has used stats tests or stats models in different settings. So you're either all being shy or or something else. I don't know. I wonder if you could just, Ilaria, Themis, give us. You talked us through some different stats tests, some different stats models. Which of the ones that you talked about come up most frequently for you in your work? Or are you using all of them a lot of the time?
I would say the t-tests. I think for what Themis has described, especially if you are kind of using, again, like simulation, or if you are using some building your own data, basically, you want to be able to perform parametric tests. Obviously, it's different when you collect data that's already available, but if you have to design your data, you would prefer parametric tests because those are, as Themis described, more powerful. So the power of the test is better. So the people that are interested in the response, they prefer parametric tests to non-parametric tests. So yeah, I mean, the quite simple, I think we didn't describe the most simplest one, which is the Z test. Like the Z score is quite useful as well in assessing difference in proportion as well. So if something changed, like a proportion changed from before and after as well, this is something that we use a lot. Parametric tests, I would say, is the preferred. But of course, if then the assumption are really like they can be sustained, then we will go to the route of non-parametric.
And talking of assumptions being met, something I often find is that transport data, crash data, it can be a bit messy. Sample size not huge, a bit tricky to work with, assumptions therefore not verified. Talk to us a bit about trying to verify assumptions and the kind of processes we might go through in doing that, and if you have any specific examples of data sets that you've worked with where it's been a bit more tricky and you've had to come up with a more creative approach.
Yeah, I think even the example that Themis was describing before, and sorry for the audience, is introducing some more testing into assessing if the assumptions are verified or not. But like the normality test is something that we may want to verify before doing, like parametric versus non-parametric tests. So probably if we can't really say from the shape of the data or the data points, we can't tell if it's quite normal or not. Sometimes you can, because it's quite intuitive. With the example on the speed that Themis showed before, it was quite evident that this was a nice bell curve. That doesn't really often happen, especially if we have fewer data points. Sometimes you may want to test this. So this is an additional test to see if the distribution is respected or not. Is it normal or is it not normal? So sometimes you want to put this into statistical test as well. And there are many tests. This adds complexity as well. Like there are different tests to check normality, for example, and you may want to use one of them. It's not really important. Like it's more getting into details on which one to use. But and we are lucky enough to live in a world where we have Python or R that can assist us to perform this kind of test. So we don't really need to worry about the formula and what's behind. More of the concept is important.
Great. All right, last question from me then. Both of you have joined TRL fairly recently, I think in the last 18 months or so, but doing previous things before that. In terms of your experience of using statistics within road safety, particularly, compared with statistics that you were using before in previous careers or previous roles, have you noticed any particular differences? I'll throw that to both of you.
Yes, I mean, from my previous work, from anyone here, I was involved in marketing, so we were basically looking at if a specific element made or not a difference in conversion rate, for example. So that's what I'm referring. We used a lot the, just Z test to check difference in proportion. And the data, obviously, because we were dealing with, emails, and as you will be aware, we receive lots of them. So it's kind of like the data sample was wider there. Like, you think about anything sent to millions of people, then you have the luxury to rely a bit more on sample size, I guess. So in here, we really need to pay attention on the sample size, and if it's small, how do we deal with that? How do we deal with outliers in a small context rather than in a, when you have the luxury of having bigger sample size? This is also something to consider, because the impact of an outlier on a small sample is not the same. So yeah, I guess this is a quick answer.
Yeah. I hadn't prepared you for that question, so all good. Yeah, Themis, anything you want to add to that?
Yeah, as for me, before being a safety consultant, I was a high school teacher, physics high school teacher. So for me, statistics played more of a role of my student test scores, I guess, but in the very descriptive analytics aspect of it.
Great, thank you. Okay, I think that's there aren't any more questions, so we'll wrap it up there. Thank you, Ilaria and Themis, for giving up your time and preparing all of that content for us. Really useful. Next webinar in the series, I'm just going to put in the chat. So marketing for this and the invite will go out pretty soon. But just before that happens, a date for your diaries. We're going to have TfL coming to join us next time to talk a bit about the stats testing that they've been using to assess the effectiveness of 20-mile-an-hour schemes in London. So it should be quite an interesting and topical one for lots of us. That webinar is going to be a bit of a two-parter, because the first part will be TfL presenting on that stuff. The second part, I'd love to answer some of your questions that you might have from the last few webinars, and potentially leading up to the next one, and then part 5 that's going to be with National Highways in December. So I'm conscious you've had quite a lot of content relating to stats testing now, 3 full webinars. There may well be questions you have about the content. There might also just be general questions that you'd love an answer to. So I'll happily sit in a hot seat, if you like, and answer any difficult questions that you have, and our TfL guests may well want to join me. So yeah, if you have any questions, any burning questions that you think, I'd really like to get an answer to this based on this series, it's a great chance to do that. So please do shoot me an email, put them in the chat now even, or just save them up for that next webinar, and we'll have a bit more of an extended Q&A to tackle some different questions in the stats that you guys want to understand the answers to. Okay, that's next time. Thanks again, Ilaria and Themis, for today. Yeah, stay safe out there, guys, and see you soon. Bye-bye.
Thank you. Thank you all.
Thank you.
Bye-bye.